Hello and welcome to part 1 of section 1 of all the PowerPoints fit to project. I'm short series in which I hope to put all of the notes down so that you can review them at home, look at them, follow them. Do more than just look at the slides and actually listen. Of course, I still recommend you go to the slides because there's animations that might help you, and also without the sound of my voice distracting you, maybe you'll pick up extra things. But because there's 32 slides in this, I am going to crack on. Light is a form of energy. Now the Crookes radiometer, small device, looks a bit like a light bulb, has got the distinction of proving that light is a form of energy. It's not in a vacuum or anything. All that happens is that the light or white side of the vein at the top there, as you can see, absorbs no heat, and the black side absorbs lots of heat. And because of this, the air expands near the black side, pushing it around. And this proves that light, which is the only thing which can be coming through the glass bulb to it, must be a form of energy. And then we have primary and secondary colours, which is one of those tack-on bits they stick on the course because they have a extra line, or they can then think they might ask an interesting question on, and they sit around trying to think of an interesting question and nothing comes up, so they just ask you what complementary colours are. So the primaries in terms of light, i.e. light projected, is red, green and blue. I know they're different from pigment. They are different from pigment. They just are. The explanation of it is quite complex and has got to do with absorption as opposed to projection. But the three colours which are called primaries in light are red, green and blue. And when you mix two of them together, you get a secondary colour. And when a secondary and the opposite primary mix together, you get white, just like when you mix the three of them together. So, for instance, yellow and blue light will give you white light. Yellow being the main one you have to kind of remember isn't a primary. So that's a secondary. So yellow is a secondary, blue is the primary, which opposite it, these are called complementary colours. Okay, now this is junior cert. Remember, angle of incidence is equal to angle of reflection. Now this is only true in what's called a plane mirror. Flat, very flat, boring, flat mirror. Any form of reflection, however, follows the laws of reflection. The angle of incidence, I, is always equal to the angle of reflection, R, but also all of these rays, incident, reflected and normal, which is the dotted line you can see there. If I can get the dotted line, there it is, that's the normal. The dotted line there, that is at 90 degrees to the surface which the ray is bouncing off of, 90 degrees in every direction. It's normal because it's not just 90 degrees there, but it's 90 degrees in every direction. That's called the normal. Okay, now some proper stuff now, a virtual image. A virtual image is one that the eye forms but isn't really there. Now, we are just totally hooked on the idea that light travels in straight lines. So if we look at a mirror, we can't visualize the fact that we're looking at reflected light. We can only see light coming from where it appears to come from. Now, as you can see, this couple are being spied on by this gentleman. The light is bouncing off of the mirror and diverging towards the observer's eye. But the observer can only see straight lines in light. So it follows the light back to a point where it appears to come from, which is behind the mirror. Now, there's nothing there. You can check. If you really don't believe me, look in a mirror and then look in the room behind the mirror and you'll find there's not the same thing. You're looking at reflection. Honestly, trust me. These are virtual images. And the most important thing to remember about a virtual image is it cannot be projected onto a screen. You can't see an image of it except in your eye. Okay, now we go for ray diagrams, which I know a lot of you do very well at ray diagrams, and I'm quite pleased at. So I'm just going to go over this just the once quickly. There you have an object. The central line is called the principal axis, and where the central line meets the concave mirror, you have a point called the pole of the mirror. A concave mirror is expressed like that. It's just a curved line. And the little lines up there, the little hatchings, if you were here, they are just to show that it's a mirrored surface. That's what they indicate. But you still, because this is physics, have to label it. You don't have to label the object, strangely enough, because the arrow represents the object. Again, simplest possible object we can think of, which shows which way it's up, is this arrow, the line with the arrow, so that's what we use. And then we draw on the rays. This is the first ray I want to teach you about. It goes parallel to the principal axis, and anything coming parallel to the principal axis comes out through the focal point. This is also true of distant light. Distant light focuses at the focal point because it's parallel to the principal axis. Okay, so you've got the object, the focal point, which is where all the light from distant objects meet, concave mirror, object, principal axis, pole. The other ray that you need to learn about is a much simpler one. It's the one which looks like it's hitting a plane mirror. If it strikes the pole of the mirror, then it will be reflected so that the angle of incidence and the angle of refraction are exactly the same. They should be equal to each other. And if we put those two rays together, that's what we get. We get an actual meeting. We get a place where the rays actually meet, giving a real image. So if I put a screen there, then I would see the image on the screen because it's a real image. The rays are really meeting. And you can see by the fact that the object is outside the 2F. Now 2F here is a very important point. This is the centre of curvature, C. It's kind of the centre of the circle of which the mirror is an arc, a part of the outside of the circle. So the distance from 2F to the mirror, that's the radius. That's the radius. And F is halfway along the radius. So they're all fairly important points, which perhaps I don't stress enough. As you can see from the diagram, we also have an inverted image. It's upside down and it's smaller. Okay, it's smaller and inverted. Here is the same ray diagram drawn exactly the same way, but we've moved the object to 2F and the image is also at 2F, as you can see from this perfect diagram, which I've obviously had to doctor to get it to look like this. Still inverted, but now the same size and still real. So we could put a screen there and we would still see it. We move the image in, the object in between 2F and F, and we get now a image outside of 2F, which is now magnified. Still real, but now magnified. Now, notice all the real images you can produce from a concave mirror are inverted. The next one, a bit of a strange one. If you put you actually at 2F, then what you get is an image at infinity. These lines are parallel to each other. They are parallel lines. They leave in a parallel direction. Still drawn in the same way, notice. Exactly the same way. The line parallel to the principal axis comes out through F. The line which is the centre of the mirror comes out as if it was a flat mirror. But now, just for construction purposes, it appears at infinity. If you look at this point, you can't focus anything. You can't, even the eye can't focus it. If you're looking at if you have a concave mirror like a spoon, and I definitely advise you to have a spoon and have a look at a spoon. You look at the spoon, and from a distance, you're upside down, and then when you bring it close, you're the right way up and magnified. Well, there's a point where it goes blurry between you being the right way up and upside down. This is when the image is at infinity. Okay, now when the image is inside F, when we've moved it inside the focal length, then we do exactly the same. The parallel ray hits the mirror, comes out through F. And the other ray comes out through in exactly the same way where the two angles are the same. Obviously, you can see I've monkeyed with this. Don't worry about that. This is purely for construction purposes, plus the fact nobody will ever question, whether you've done the angles right. It's merely they're looking to see whether you know what should happen. Now, again, like the plane mirror, the images are diverging. So if I'm looking from down here, if this is where my eye is, down there, and I'm looking in that direction, I see the rays diverging from this point. You see, the rays are coming from over here, from this side. Now, that's behind the mirror where the light doesn't go. So the image isn't real, it is virtual. The rays do not really meet and you cannot project it onto a screen. It is, however, upright and magnified, making it a very useful image, but still not a real image. Now, in a convex mirror, instead of the light coming back through the focal point, it comes away from the focal point, which is on the other side, the minus side. So it basically emits itself from there. That's the difference with a convex mirror. And in the same way, the rays appears to diverge. So wherever I look at from over here, my eye's over here somewhere, I'm looking at the image. I'm looking at diverging light. So my eye constructs an image behind here, which as you can see is smaller, virtual and upright. So quite different from the previous one. And it really doesn't matter where I put my object, whether it's inside or outside the focal length, I still get this virtual image which is diminished. And now this ray diagram is definitely worth remembering. I would remember one of the ones from the previous mirror, maybe two. I'd remember one outside the focal length, one inside the focal length, and any of these three. These are the three I'd remember because you can adapt these also when you're doing lenses. So you really only have to remember three. And sometimes you only have to remember the way the rays are drawn, and that is plenty. So how do we use curved mirrors? Well, we use them for magnification. Dentists use a little concave mirror with a slightly longer focal length than your mouth so that when they look in your mouth, they can see an upright image magnified of your teeth. The same for the same reason and in the same way, makeup mirrors are used. Convex mirrors, on the other hand, are used to give a greater field of vision. So you can see more by looking in the mirror. You look in the mirror and you can see a greater field than you would if it was a flat mirror. You can see a greater area. They use them for security mirrors and for rear view mirrors so that you can see, you know, a greater thing behind you. So you don't just look right behind the car. You can see like 2 or 3 lanes behind the car. They increase the field of vision. Okay, the bit you hate. Calculations. Well, first of all, here's the formula, which you do not have to remember. This bit, however, I would encourage you to remember what the letters actually mean. That's important. F is the focal length. The distance here. You see what I'm drawing? There. The distance from the focal point, F, capital F, to the mirror is little f, the focal length. Now, as I say, this is the point where all distant light focuses. So if you're shining light from the window, this is where the light would focus. This is where you would get the image if it was far enough away. Images of stars, for instance. The object distance is u. That's the distance from where the object is placed to the mirror. And the image difference is v. So this is our first example. It's the same example I've used in the PowerPoints. I will obviously do other questions to fill this in, but I'll just read through it. An object is placed 20 centimetres from a concave mirror of focal length 10 centimetres. Find the position of the image form. What's the nature of the image? Now, what this is asking is simply doing a bit of maths. Okay, and to do the maths, you need the formula. But before you even start that, you have to know which one's which. Now, focal length of 10, that's easy. The image is placed 20 centimetres from the concave mirror, that's U. So we write down our F and our U. Once we've done that, the next thing we do is to write down the formula. Now, unless you're an absolute gold-plated genius, look it up in the goddamn logbook. There. And we don't just look it up, we write it down. Because what you'll find when you do this in any exam is a little 3 written next to it, which means you got marks for this. You got marks for looking up the formula and writing it down. There's no memory involved. This is a page flick and transmission. Anybody can do it. I could teach a 4-year-old how to look up a formula and write it down. So that's what you should do. Only then, when all those stages are done, do you place the numbers where they should go. The F replaces the F there. The U replaces the U there. And our unknown, therefore, is V. We place them in. Now, because the unknown is on the same side as this number, this has to move to the other side where it becomes minus. We then put this in our calculator and we receive this result. 1 over V is equal to 1 over 20. But it's V we want, not 1 over V. So V is equal to 20. Now, because it's positive, that makes it a real image. So that's the nature of the image. It's real. Then we have to work out the magnification with a so-called German formula. And if you don't remember why it's called the German formula, I'm not going to be stupid enough to record myself making a comment like that on here. M is V over U. Right, now again it's in the logbook. Now what I've omitted here, just for simplicity, is these two lines. Beautifully drawn, as you see. I think they should be a little bit wider apart to make it look like a line on a railway waiting for a truck to come. The two lines mean modular, so you don't worry about the V or U being positive or negative. They're both positive in this formula. Now, as they're both 20, it means that the image is a magnification of 1, i.e. the same size. If M was equal to 4, it would be 4 times the size. If M was equal to a half, it would be a half the size. This is the image we're talking about. The image would be 4 times the size. The image would be half the size. That's what M means, the magnification. Okay? An object is placed 20 centimetres in front of a concave mirror with focal length 30. Find the position of the image and the nature of the image formed. So first thing is, U is equal to 20. F is equal to 30. We write it down. We write down the formula. 1 over U plus 1 over V. Okay, it's a concave, so we don't have to worry about the focal length being negative. We put the numbers in. 1 over 30 equals 1 over 20 plus 1 over V. And then to get 1 over V on its own, we have to say 1 over 30 minus 1 over 20. Then we do the calculation and we get 1 over 60, but minus. This means that V is 60, but the image is virtual. Virtual, because of the minus here. And we also have to write centimetres before we forget. So that's how we do the questions. And I think they're really easy, particularly the bit here, because you use the calculator. Now, one more question. An object is placed 20 centimetres from a convex mirror. Convex. This means that we have to have a negative value for the focal length. The focal length is negative because it's convex, because the image appears to come from behind the mirror, because the effective focal point is behind the mirror. So that's minus 30. Now the object is still positive. It still has to be in front of the mirror or else it doesn't work. But in this case, V is always going to be negative. So if I just do the calculation again writing down the formula, we always write down the formula, always in physics. 1 over minus 20 equals 1 over 30 plus 1 over V. So again, 1 over V equals 1 over minus 20 minus, what am I talking about? 1 over 30 minus 1 over 20, because that still comes over and becomes minus, minus 30 minus 20. That's correct. I had it right the first time around. What the hell am I doing? I'm going mad. Okay, well, it's still over 60, but now instead of, you've got 5 over 60, minus 5 over 60. Just do it on the calculator. Don't try and remember it, which is the same as 1 over minus 12. So V is equal to 12 centimetres, but the minus makes it virtual. Perfect. Now, the M in this case, okay, we've got a U of 30 and a V of 12. So 30 and 12. So if I just do this, the M is equal to V over U. And as I said, that's a modulus. So instead of minus 12, we simply write down 12 over 30, which is smaller, which is what we'd expect, with a convex mirror. So if the original height is 10 centimeters, that's the height of the object, then the height of the image will be 10 times 12 over 30, which is, as anyone will tell you, 4 centimeters. Smaller than the original 10 centimeters time. This is the experiment, this is the diagram. Notice that I've drawn the lines U and V in as well as the object. This is to show where you measure the distances from. You have a lamp box generating the light, a luminous object, cross wires, which are essentially what you're focusing. You have the concave mirror, which is labelled, and the screen also, which is also labelled. So very careful, draw everything in, label everything. You know about that principle. And then finally, the two questions I'm going to set you. This one is a fairly easy one, not something that will cause you an awful lot of trouble. You can see here the focal length. It does say, however, that the copper sheet, the object was only half the size. This means M is equal to a half. Now, if M is equal to a half, then you can always, that's also equal to V over U, for instance. So U is equal to 2V. That's the clue on that one. You still have focal length of 60. Have a crack at that. That's from 2007. Okay, this one is from 2014. As I said, I'm only going to set things in the last from 2012 because that's when the examiner sort of changed, the system changed so that the questions are slightly different. The clue on this one is to find that the diameter of the decoration is 20 centimeters. It's 20 centimeters in diameter. That means the radius is 10 and F is 5 centimeters. A quarter of the diameter, half of the radius. But it's a convex lens. Look at it. It's convex, meaning the focal length is minus a half. I hope that's a help and you can get on and do that one. Let's see how it goes. Next, it's going to be the classic subject of refraction, which should be a slightly shorter one, followed by a shorter bunch of questions. Thank you.